Okay, hello everyone. My name is Jian-Xun. I'm assistant professor of aerospace and mechanical engineering from University of Notre Dame. So here I would like to present our recent development on the flow super resolution and denoising using physics-informed convolutional neural network, where the high-resolution labels are not required. So a little bit about the background and motivation. We know the high resolution flow data are very useful for scientific investigation and discovery in many applications. However, the fluid data are usually sparse, incomplete, and noisy in the real life scenarios due to the following reasons. So first, we know the flow data are typically large-scale spatial temporal fields, and thus it pose significant challenge to data analysis, sharing, and visualization due to limited storage space and large communication overhead. For example, like the DS of the wall-bounded turbulent flows at a Reynolds number of 10,000 can generate more than 20 terabytes files at each time step. And the file size will still like increase exponentially as the Reynolds number grows. Therefore, scientists could only afford to store a small fraction of data, like a temporarily sparse sequence, spatially downscaled volume, or a selected variable subsequence for the post hoc analysis, right? And the second reason is data resolution is often limited by the capability of the measurement techniques. For example, we know the 4D flow MRI, the magnetic resonance imaging, have been widely used to quantitatively study the cardiovascular blood flows. But the spatial resolutions and the signal to noise ratios, SNR, of the flow MRI data are far from sufficient, limiting their clinical applications. Therefore, it is significant and imperative to enhance resolution and reduce the noise level. So this is actually here referred to as the flow data super resolution and denoising. And moreover, we know the fluid flow data, even with a high spatial temporal resolution, are usually sparse in the parameter space due to a limited computational or experimental resource. For example, a single run of the fully resolved DS turbulent flows often takes days or even weeks on the high performance computing facilities. And you can imagine it becomes infeasible to perform the massive queries in the parameter space to explore many different boundaries, geometries, and operational configurations for the UQ and optimizations. So in those scenarios, um, the data super resolution in the parameter space can be treated as a cost-effective surrogate model that leverage the use of the efficient low resolution simulation or experiments. So the growing success of the deep learning based image super resolution in the computer vision inspires the application of the deep neural networks for the flow field super resolution and reconstructions. So conceptually, the low resolution data um, can be fed into a neural network as the input, and the neural network will output the corresponding high resolution flow data. So despite the great promise has been demonstrated in recent publications, the success of this deep learning model mainly relies on a large amount of high resolution labels, high resolution data as the labels. Since we need a sufficient high resolution label to train this neural network. However, the thing is, the high resolution label are usually scarce or even not available in many cases. For example, if you want to super resolve the 4D flow MRI imaging, we really don't have the high resolution MRI data, since this is because the resolution limit limitation of the MR imagers. However, this mapping is not pure a black box to us. Instead, we know the underlying physics, meaning the network output should satisfy the conservation law of mass and momentum because it's a flow, it's an incompressed flow, and it has to satisfy the divergence-free conditions and momentum conservation equations. So we can actually use this no physics, the governing equations, and boundary conditions to constrain or even drive the neural network training. So we may not need many high resolution labels, or even we can do the super resolution without any high resolution labels. So this idea is known as a physics-informed or physics-constrained deep learning. For example, we can formulate a point-wise the physics-informed neural network, aka the mean, the PIN, the PIN. So it takes the spatial and temporal coordinate as the input and output the corresponding flow solutions in a point-wise manner. So the training is constrained or even driven by the conservation law of the fluid flows, which is the Navier-Stokes equations. And the low resolution or sparse flow data can be assimilated as the training labels as well. So usually this optimization is formulated in a deterministic way where we define the loss function and to minimize the violation of the conservation law. However, since the low resolution data or sparse data are usually noisy as well, so sometimes this physical model may also contain the model inadequacies, may have the model form uncertainties. In order to consider this uncertainty and make robust, to do the robust flow reconstruction, and we develop a Bayesian formulation where the physics-informed likelihood function is constructed and the posterior of the neural network parameters or weight approximated using a non-parametric variational inference approach. So specifically, we minimize Stein discrepancy, which is kind of equivalent to minimizing the KL divergence or maximizing the elbow in a non-parametric way. Moreover, instead of imposing the boundary condition as a penalty term here, we modify the output layers by encoding the boundary conditions in hard manner. Namely, the initial and boundary condition will be automatically satisfied by the network construction. So, for example, here we want to reconstruct the flow field of the stenosis vessels, like this one, and using this sparse and noisy flow measurement. Is quite sparse and also noisy, and this is a ground truth. So the purely data-driven learning would fail because it's pretty sparse and noisy, and you can see the reconstructed flow field is more like a rendered field and not physical at all. In contrast, our physics-informed Bayesian learning can accurately reconstruct the flow and agree with the CFD ground truth pretty well. And then in the meantime, it also provides the predictive uncertainty since our network is formulated in a Bayesian fashion. So let's check if the estimated uncertainty also makes sense if we change the data noise. So for example, if we use the noise-free data, and you can see the prediction uncertainty is very low and it's all zero in the most regions. And if the data noise is increased to 10%, and the uncertainty of the prediction also significantly increased, right? So if we further increase the data to 20%, the standard deviation of the prediction is also doubled from 0.005 to the 0.01. So if we check the mean predictions for the different cases, they are all similar for this all three cases with and agree with the CFD reference, the ground truth very well, showing the robustness of the variational Bayesian formulation for the flow reconstruction. However, we know the pointwise physics informed learning based on the fully connected neural network, aka the PIN suffers from the scalability issues due to its pointwise nature. The training cost of the PIN will significantly increase for complex problem, especially with parametric variations, since the PD residual need to be evaluated on a massive amount of the collocation points in a high-dimensional input space. So to enable the efficient learning of the problem with a large-scale spatial temporal solution field in the high-dimensional space, the convolutional neural network, aka the CN structure, has attracted increasing attention in the scientific machine learning communities. Compared to the fully connected nets, the CN usually needs order of magnitude of fewer parameters because of the parameter sharing via the filter-based convolution operations, which is well positioned for a large-scale and high-dimensional surrogate modeling problem and the super resolution problem. So here we developed this physics-informed super resolution CN. So the input of the model this time is a low resolution flow field, and the output is a super resolved flow solutions. To formulate the physics constraint loss function, we use the Navier-Stokes equations boundary condition to impose the physics, the flow physics. And the low resolution data also can be, here the low resolution data also can be leveraged to define the low resolution data loss component by downsampling the super resolved network output. In contrast to the pointwise, the fully connected formulation, here the entire discrete solution field on the rectangular domains can be approximated by the convolutional neural network. So it will enable the image-based end-to-end learning and can directly generate the super resolved flow field over the entire domain instead of the pointwise outputs. Therefore, they often have much less training cost and have better predictive accuracy. I can show you later by using the results. So first, here, let me show you some examples of the super resolution results of this kind of flow passing a square duct with complex inlet profiles on the right edge, on the left edge. So on this left column, you can see those are low resolution and noisy velocity fields with the different inlet. So they actually provide very little information because of large noise and a very low resolution. And using the traditional super resolution approach, like the bicubic upsampling, and you can see the results are unsatisfactory, and most of them are not physical. However, our physics-informed CN perform much better and agree with the ground truth very well. If you look at the streamline plots and all the flow features, like the recirculation on the bottom, and can be captured very well, and it agree with the ground truth pretty well. So remember here, no high resolution label actually are used to train this super resolution CN network. Okay, so it's more like a label-free super resolution CN. However, here we have another problem. We know the classic CN has originally been developed for the image recognition and processing, where the convolution filters are designed for the image or image-like data. That is why you find all the existing work on the PD-constrained CNN are only able to deal with the problems defined on this rectangular domains, rectangular geometries, and with uniform meshes. And they cannot go beyond the regular image-like domain because of the intrinsic limitation of the classic CNNs. However, we know in many practical applications, the geometry is way complicated than rectangular, and which need the non-uniform meshes all the time, like the patient-specific arteries, vessels, and the flow past the complex automobiles with very complex geometries and others. So now the question is, how can we still leverage the CN for this problem with the irregular geometry and non-uniform grades? So as I said, the classic CN cannot directly handle the irregular domains with non-uniform meshes. And even for this simple irregular geometries with boundary fitted meshes in this figure. So a classic CN are not directly applicable since the coordinate frame is non-Euclidean. So the shaped invariance that justifies the use of a classic convolution operation is no longer valid here. Although we know the new convolution filters can be defined for a given non-Euclidean space, like a lot of people are develop the graph neural network in the geometric deep learning, but how to generalize them across the different domains and different topologies, and how to construct the different operators for the physics based loss function are still very challenging. So to enable the use of the classic CN backbones, usually people will do this so-called rasterization, okay? Try to pre-process the data in the most data-driven CN scenarios. So it converts this irregular domain, irregular shape, into this uniform grade images. And the geometry is typically represented by the binaries or sign distance functions, as shown in this figure. However, this formulation fails to update in the physics constrained learning due to the following reasons. First, we know after rasterization, the boundary shape becomes this kind of stepped and zigzag, which introduce a lot of aliasing errors under this low or moderate image resolution. Especially when it comes to the boundary value problem, even a minor misrepresentation of the boundaries may lead to large errors in the learned solution field. And second, use this so-called binary or sign distance function representations. It's difficult or even impossible to impose PD boundary conditions. And therefore, the physics constrained learning would fail, particularly when the label data are scarce or even absent. And moreover, when the shape of the physical domains, like this blue region, is far from the corresponding rectangular envelope. So the artifacts introduced from the background regions may complicate the training process and make the optimization easier to trap in the bad local minimum. For instance, if this is like a binary-based representation of the shape, the derivative computed in the background is all zero. So the PD are exactly satisfied, but which is clearly not the solution we want to search for, right? So although sufficiently high resolution can reduce the representation area and elevate some of the alpha mentioned the issues to a certain extent, I would say, but it will significantly increase the training costs and cost of memory issues. And lastly, we know this conventional rasterization or the voxelization methods are not differentiable with respect to the input design space. So it's going to limit its use for the geometry optimization, and uh, if you go for the design purpose, and it's gonna limit those applications. So therefore, we propose a novel physics-informed geometry adaptive CN approach, and we call it PhysioGeoNet. Here, it will enable the use of powerful classic CN backbones for the physics-constrained learning on the irregular geometries with non-uniform meshes. So the key idea is to utilize the coordinate transformation techniques to map the solution field from the irregular physical domain into this rectangular reference domain. For example, the left side is a physical domain and with the coordinate x, and the right one is the rectangular regular reference domains with the coordinate c. So if we can define a one-to-one mapping between those two coordinates, meaning we know either the forward map from the reference domains, to the physical domain, or the inverse map from the physical domain to the reference domain. So we should be able to formulate the PDEs on the reference domain, and the PDE loss function can be defined on the reference domain instead of the irregular physical domain. Therefore, the classic convolutions can be used. However, in most cases, analytical form of either this forward or inverse map G or G inverse are not available for any arbitrary geometries. So we have to approximate numerically. How to do it? Well, think about it is that the boundaries of the geometries is null, right? It's given or null in both the physical or reference domains. In the reference domain, it has to be a rectangular, and in the physical domain, you know the geometries. So therefore, we can actually define a boundary value problems, meaning to solve elliptic equations and with a specific boundary, so that the internal one-to-one mapping with G can be uniquely obtained numerically on each mesh node. For example, we can choose to solve Laplace equations on the physical domains to obtain the inverse map. However, this is not very practical, since the set of the uniform grids that corresponding to the physical boundaries are really unknown. Instead, it is more practical to solve this forward map, which locate the corresponding collocation points in the physical domains, and given the uniform mesh grid in the reference domains. So by interchanging the independent dependent variables, and we can derive this diffusion equations in terms of the physical coordinate. So by solving this equation numerically, the discrete values of this forward map G are obtained. So this is a deterministic one-to-one coordinate mapping, so no aliasing errors will be introduced. Moreover, this mapping can be pre-computed, so it won't introduce any overhead or for training the neural network. That's a good thing. So to enable the physics constrained learning in the reference domain, the original PDE defined in physical domain can be has to be recast as a form in the reference domain. Specifically, we need to compute the Jacobian of this transformation map G, and to convert the differential operators from the physical domain to the reference domain. So finite difference are used to numerically compute the Jacobian, which has to be performed in the reference domain. So we derive the inverse transformation for all the spatial derivative terms, like the partial x, partial y, and to the reference domain. As you can see, the Jacobians and all the other matrix between the two set of coordinates can be pre-computed. So which becomes a constant in the newly formulated PDE loss. So to obtain the second or even like higher derivatives, we can actually use the finite difference based CN filters and apply them for multiple times instead of using the chain rule to overcomplicate the implementation. So now the PD-driven optimization is reformulated on this reference domain. So you actually can perform the physics constraint learning using the classic CNNs on the reference domain. So it doesn't matter because the reference domain is a rectangle and it has a uniform grade. All right. So here are some results I would like to show you. So the left are the low resolution flow MRI fields and with the noise. So upper one, you can see is corrupted with the Gaussian noise. And the lower one is actually corrupted with the MRI noise, which is definitely non-Gaussian. If we directly use the bicubic interpolations to super resolve this low resolution MRI flow data, the results are pretty bad and not physical at all. However, our CNN super resolution solutions can eliminate large Gaussian or even the non-Gaussian MR noise and agree with the reference pretty well. Remember here, we didn't use any high resolution labels to train our neural network. So in some cases, if you don't know the boundary conditions, you only know, okay, the flow is governed by the Navier-Stokes, but you don't know the, for example, you don't know the inlet velocity. The inlet velocity profile is not known, it's not given. So it's pretty common in the clinical practice because sometimes we don't know the boundary condition for the flow. But on the other hand, we may have some sparse observation data like the flow rate on these 4 slices, and which could be obtained from the 2D PCMR. So this is pretty common in the cardiovascular application. So you can do the 2D PCR MRA on the limited number of slices, right? So our learning framework can actually unify this forward super resolution and inverse inference of this unknown boundary conditions by assimilating this additional observation data. As you see, the forward super resolution, super resolved flow agree with the ground truth pretty well. And at the same time, the inlet velocity profiles, and which the truth is parabolic profiles, and can be accurately inferred as this blue dot is our inferred inlet. So they agree with the true inlet very well. And lastly, I would like to show you that the trained network can rapidly super resolve the low resolution flow field to the high resolution ones in a high dimensional parameter space. For example, the low resolution velocity field obtained by randomly sampled the inlet profiles in a 20-dimensional parameter space. So this inlet velocity profile is a random field, and we use the KL expansion with the 20 mode to represent this random field. Similarly, although no high resolution labels are used, our super resolved flow fields, the CN super resolved flow field, agree with the ground truth pretty well for this randomly selected 16 samples. So you can imagine that the scientists can opt to run their simulation or do their experiment at a low resolution, and then upscale the result back to the target resolution, which will significantly save the costs and the speed of the process of scientific investigation and discovery. So let's compare the fully connected PINN, the PIN, with our proposed physics-informed CN. So if we fix the training budget, meaning we train both networks for the same amount of time and approximately same number of iterations, about like 1,000 iterations. So you can see that clearly our physical GeoNet already accurately capture and learn the solution for both the velocity and the pressure. In contrast, the fully connected PN only learned the trend for the velocity, but with the large arrows, and it basically failed to capture the pressure at all. And so then, if we train the Bose network with a sufficient number of iterations, and you can see that our physics GeoNet only need about 1,000 iterations to converge, while the fully connected PN need 10,000 iterations. Even so, the accuracy you can compare is much lower than our CMs, and it still fails to learn the pressure distribution. It demonstrates our proposed approach. Our proposed approach is more than 10 times faster for training and is more accurate. Here I would just like to list our recent publications on this topic, including the flow surrogate modeling and for the Navier-Stokes equations, Bayesian physics informed neural network, CN formulation for the irregular geometries, and super resolution of fluid flows. So if you are interested, please download it from my website. All the manuscripts are available, and also like the code are available on my GitHub, and you can download and play with it. All right, so this is about the presentation. Thank you.